Welcome to this discussion about comparing linear and exponential functions. So this will be one of probably 4 quick videos about this skill. In the first video here, we're going to talk about the difference between the actual equations when they are in standard form and how to tell them apart and what their specific components represent. So here's a couple of equations, and you've seen these before. We've talked about linear equations and we've talked about exponential equations. So you probably know that this one here is a linear function, right? And we recognize it because x is not raised to any power. Often you'll find it multiplied or divided by something. And also we could see something added or subtracted to it. But the important thing here is where the variable is, which is x, it's raised to the first power. Okay, so what are the parts of this function? Well, the first part here, m represents slope. So m represents the slope. And slope can be thought of if you were to identify 2 points on the line that is the graph of this function. It's the average rate of change between the y values and the x values. Okay, so we can use our slope formula. Remember, y2 minus y1 over x2 minus x1 to calculate the slope. We can also, if we're given a graph, count the rise units over the run units between any 2 points on the graph. The thing about a linear function is that the rate of change between any 2 points in a linear function will be the same. And that is unique to linear functions. Okay, so there's your variable, right? We already talked about that and what is important about the variable. And then b represents the vertical translation of this linear function. And this will give us the value of the y-intercept. So we're putting together a lot of concepts here. Remember that the parent function of a linear function goes right smack dab through the origin. So the b value, which is the y-intercept, will represent how much this function has been shifted up or down. And when we're talking about linear functions as functions of time, that would represent our initial value, where time is 0, the initial value of the function when time has not started ticking yet. All right, and so let's look at this one over here. This would be our exponential function. And we've got, again, 3 main components here. So this works a little bit differently than a linear function. The vertical stretch will affect the y-intercept. Okay, and the reason that is because if you were to think about this function here, think about putting an x value of 0 into the base. Now, it doesn't matter what this base is. Anything to the 0 power is going to be 1. Right? For any exponential function, when I put a 0 in here, the y-intercept, which will be a every time. Okay? And again, if we're thinking about an exponential function as a function of time, and we often do that, this would represent our initial value. Sometimes you've seen functions like a equals a naught times e to the rt or e to the kt. These are all exponential functions where this part right here, and sometimes we'll say this is a naught, that just means a at time equals 0. Okay, and so whatever's in this position before the base that's being raised to the power is our initial value, or it's our y-intercept. The base here represents the multiplier, or what you have to multiply to get between consecutive x values what do you have to multiply your y value by to get to the next y value between consecutive x values. That is a little wordy, but it will make sense when we look at tables and graphs, okay? and x is the variable, and you can see where it's located. In an exponential function, it is in the exponent. And so everything else would be filled in here. That's the only thing that would be left as a variable besides the y, of course. Okay, next video we're going to talk about how we can look at tables and recognize what they represent. See you then.